Hi everyone. Today's introductory topic in preparation for the Calculus 1 course are going to be logarithmic functions. The logarithmic function in base a, which must be a positive number and different from 1, is defined as the inverse of an exponential function with same base. More specifically, if f of x is the exponential function with base a to the x, and if g of x is the logarithmic function in base a applied to x, then their composition, f of g of x and g of f of x, will both give x. So again, we're referring to information we gave earlier about inverse functions, which is that one will undo the effect that the other has on x. So basically, when you have a to the power log in base a of x, the operations cancel off and return the original x value. Likewise, applying a logarithmic function in base a to the x will cancel off the operations and return to the original x. If you want to use an analogy, think of this as rooting x followed by a square on the root of x. You'd have mutually canceling operations. The logarithm helps answer the question, what is the exponent such that? For instance, computing log in base 3 of 27 answers the question, what is the exponent that must be applied to base 3 such that the result will be 27? In other words, whatever number will result from the log in base 3 of 27 is also the number which applied to base 3 in an exponential function will give 27 as an answer. For example, compute log in base 5 of 625. Well, first approach is to think of 625 as being a power of 5. In fact, it's 5 to the power 4. And recall the inverse relationship that logs and exponentials have to one another. So a logarithm in base 5 applied to 625, or a log in base 5 applied to an exponential 5 to the power 4, well, the logarithm and the exponential are mutually canceling, which will give 4. As a second approach, we can reverse the equality from a logarithmic form to an exponential form. Whatever number x is equal to log in base 5 of 625, then that same number applied to the power of 5 should give 625. By trial and error, we can then figure out that x is 4. Now, in most cases, it will be very difficult to calculate a logarithm, and we will not be able to find them just by guessing. The calculator will obviously be quite helpful. Here's an example where we're going to use properties of exponentials and logarithms simultaneously. So let's find the numerical value of the log in base 2 of the cube root of 16. Now remember that logarithms in base 2 are well related to exponentials in base 2. So what we're going to try to do is rewrite the cube root of 16 as a power of 2 somehow. 16 itself is 2 to the power 4. Cube rooting is equivalent to using a fractional exponent 1 over 3. And consecutive exponents can be multiplied. So essentially, applying the log in base 2 to the cube root of 16 is the same as applying a log in base 2 to 2 to the power 4/3. Now we have a logarithm and an exponential, which are in a composition both with base 2 and therefore are mutually canceling operations. So this will give 4 over 3. Again, here's an example where we're going to use properties of both logarithms and exponentials. Okay, so first and foremost, trying to simplify the expression log in base 5 to 5 to the power x over the y-th root. That sounds weird, doesn't it? The y-th root of 125. Our mission here will be once again to somehow rewrite all the exponential terms as powers of 5 so that we have a common base with the logarithm, whose base is also 5. Okay, so 5 to the power x is already in base 5. 125 is actually 5 to the power 3. The y-th root, assuming y is not 0, is equivalent to the fractional exponent 1 over y, and I've already done the step of joining the consecutive exponents 5 to the 3 to the 1 over y as 5 to the 3 over y. Still within the argument of the logarithm, we've got a division with terms whose bases are 5, and in that case we can subtract the exponents. And there we go, we've done our job of expressing the entire argument within the log in terms of powers of base 5. And now the logarithm in base 5 and the exponential in base 5 are inverse functions and therefore cancel one another off. And therefore x minus 3 over y would be the outcome and the simplified version of the original expression. Some special cases in terms of notation. When the base of the logarithm is 10, it is conventional to write log x without actually specifying that the log is in base 10. So for instance, log of 1,000 can be interpreted as log in base 10 of 1,000. And since 1,000 is 10 to the 3, log in base 10 and the base 10 exponential would be mutual inverses and cancel off to give 3. When the base of the logarithm is e, so the natural number, the Euler's number, it is also conventional to write ln of x rather than log in base e. ln of e to the power 5 would be 5 in this case, since ln is presumed to represent a log in base e. Once again, we have a logarithm and an exponential with the same base, which end up playing the roles of inverses. Graphs of logarithms can be traced by inverting the roles of x and y from those of the corresponding exponential function. For instance, the graph of y equals 1/3 of x, seen in our previous video, showed an exponential of decreasing nature with y equals 0 as a horizontal asymptote. The graph of the logarithm in base 1/3 of x would interchange the x's and the y's and now have a vertical asymptote at x equals 0. Notice how the exponential function crossed point 0, 1. The logarithmic function crosses point 1, 0. If you want to focus on another point, you can perhaps look at minus 2, 9, which was a coordinate point of the exponential function, and 9 minus 2 is a point of the corresponding inverse logarithmic function. In the previous video, we also examined 4 to the power x as an increasing exponential function, also with y equals 0 as a horizontal asymptote. The graph of log in base 4 would also be increasing and now have x equals 0 as a vertical asymptote. Again, you could use some reference points from the exponential function and notice how the x and y coordinates are interchanged to produce the logarithmic function. The domain and the range of logarithms are therefore reversed relative to those of the exponentials. The domain of a logarithm consists of all positive values of x, excluding 0. The range consists of all real numbers. The vertical line x equals 0, that is the y-axis, is a vertical asymptote of logarithmic functions in base a. Notice how, regardless of the base, x equals 0 is a vertical asymptote. Because of their inverse relationships, logarithms are used to solve equations where unknowns appear in the exponents. For example, let's solve the equation 10 to the power 5x plus 3 equals 200. Notice how the unknown appears in the exponent of a base 10 exponential function. Since the base of the exponential is 10, it would make sense to apply a base 10 logarithm to both sides in order to solve the equation. So here is the equation we're trying to solve. Because the two sides are equal expressions, performing the same operation on both sides maintains their equality. So here we're applying a logarithm in base 10 to both sides. On the left, observe that a base 10 logarithm and a base 10 exponential are inverses and therefore mutually cancel off to give 5x plus 3. On the right-hand side, log of 200 is a number that we don't have necessarily a handle on. So let's just think of it as a number, period. And then we can subtract 3 and divide by 5. Your calculator will give you a rough estimate of what x is. It's worth replacing x by your solution in the original equation to validate that the answer is actually accurate. Likewise, keep in mind that exponential functions act as the inverse of logarithms. Hence, they should be used to solve equations where the unknowns are contained in the logarithms. For instance, here we have an equation, log in base 3 of 2x minus 1 equals a half. Now, the only way we will isolate x will be to find a way to eliminate or to get rid of the log in base 3. Now, since the logarithm is in base 3, it would make sense to apply a base 3 exponential to both sides. So once again, here are two expressions that we are assuming are equal, and therefore if we use both as the exponent of 3, their equality will be maintained. Now the reason why this will work is that we now have a base 3 exponent on the left with a base 3 logarithm, and the mutual inverse relationship that they have would simplify that combination or that composition to 2x minus 1. On the right, 3 to the power 1/2 is like square rooting 3. And then we can add 1 and divide by 2. Once again, a numerical approximation can be obtained from your calculator, and you can double check your answer by replacing x by the solution you've obtained in the original equation that you solved.